counting your way to the binomial theorem. Right, first we're going to look at how many different ways you can arrange an object. Here we have an object alpha. How many ways can you arrange the object alpha? One, of course. Well, let's add another object. And you can imagine these objects standing in line, alpha and beta standing in line. How many different ways can alpha and beta stand in line? Well, alpha could be in front of or behind beta. So there's just two possibilities. But we haven't really generalized yet. Let's take a look at three possibilities. Now, from the previous two possibilities, I had alpha and beta, or I had beta and alpha. When gamma comes along, gamma has three possible positions that gamma can go in. Gamma can go in the beginning, in the middle, or at the end, in either of the two situations where we had alpha, beta, or beta, alpha. So now, looking at the diagram, we can see that we have 1 times 2 times 3, which is equal to 6. And now we can generalize this idea to n objects. If I have n objects, there are 1 times 2 times 3, all the way up to n different ways to arrange those objects. All right, now what happens if some of those objects are indistinguishable? In other words, if you open up a bag of M&Ms, we're going to say that all the M&Ms are the same color. You can't tell apart. So here I have listed out the 6 different ways to arrange 3 objects, but now we're going to turn the gamma into an alpha. And when we turn the gamma into an alpha, 2 of the previous ways to order collapsed into 1. And you can see this happens as I turn the gamma into alpha. But a question we could ask here is, how many different ways can we arrange the alphas? Even though we can't tell them apart, we could ask, how many different ways could we arrange them if we could tell them apart? And the number here is 2, because I have 2 alphas that I can't tell apart. This goes in the denominator. This is how the results from the left-hand side are reduced. Okay, so now we can generalize this idea. If I have n objects and k sub 1 of them are indistinguishable, it is n factorial over k sub 1. Now, why k sub 1? Because I want to generalize to the next stage, where I have a whole bunch of objects here. I have 7 hearts, 5 frogs, and 9 yellow widgets. And I want to know how many different ways can I arrange them. So I'm going to align them up in a line. And of course, we're assuming that the frogs don't jump away. So the question, how many different ways can I arrange all of these quantities if I can tell them apart? Well, that would be the total number of objects, which I put in the numerator, 7 plus 5 plus 9, factorial, but then I divide it by the things that I can't tell apart. Well, there are 7 hearts I can't tell apart, so I got 7 factorial in the denominator. 5 frogs I can't tell apart, 5 factorial in the denominator. And still, look at the huge number that I get. So with just this small quantity of objects, there are more ways to arrange these 7 hearts, 5 frogs, and 9 yellow widgets than there are people in the world. That's pretty amazing. All right, let's write this down in a general form. And what we have here is I'm going to have multiple groups. In this particular example, I have 3 groups, and in each group I have a certain number of objects. Well, let M represent the number of groups that I have, and K sub J equal the number of items in each group. So K sub 1 here would represent the number of hearts. K sub 2 would be the number of frogs, all the way up to K sub 3, because I have 3 groups, would be the number of yellow widgets. And all this thing up on the top is telling me to do is it's just simply telling me to sum up all of the number of items in each group. And when we sum this up, I take the factorial and I get what's in the numerator. In the denominator, I do the exact I take the number in each group, I do the factorial, and I multiply them all together. So we have a general relationship here. Okay, now let's apply this to expanding powers. Here I have a plus b squared. I'm sure we've all done this before. We can break this out into a squared plus ab plus ba plus b squared. Now, normally we combine those two middle terms to the expression below. Well, we can ask ourselves, how many different ways can two A's be ordered? Well, the two ways I can't tell apart, so there's only one way. How many ways can you arrange an A and a B? There are two ways to arrange the A and a B. So notice the ways in which we can arrange the coefficients here are I mean, the ways in which we can arrange the A's and B's are the values of the coefficients in front of there. Let's do it again. Let's go A plus B to the third. Now we can expand this out. It takes a little bit of time, but we can certainly work this thing out. And now once we simplify this, again, we can ask the same question. How many different ways can you arrange three A's? There's just one way to arrange three A's, because if you take three A's next to each other, they're all indistinguishable. If you rearrange them, you can't tell that they've been rearranged. But how many ways can I arrange two A's and one B? There are three ways. If you use the equation from the previous, you'll get three. All right, well, let's generalize this. Here I have A plus B to the nth power. Well, let's start looking at some of the properties of this. Okay, there's a lot of garbage here on the screen here, but let's figure out what's going on. First of all, we know that we're going to have an A to the n somewhere, and then a whole bunch of terms as we work our way down to a B to the n. And in the middle, we have terms that at each term, the A drops a power. Let's go back actually one slide and take a look at this. If we look at the A to the third, we get A to the third, and now the next term, A is only to the second power, and B comes up one. And now A is just to one power, and B comes up another, and now it's B squared. And this is exactly what we see going on here. The A drops a power in each one of the terms as we go down until we have A to the first, and then of course A is gone. And the B comes up a power in each one. Now, let's look at this middle term here and ask, how many different ways can we arrange n minus m A's and m B's? Well, what is n minus m plus m? Well, it's n, of course. So up in the top I have n factorial. And this makes sense. I'm doing my power to the n, so it's n factorial. Now, how many A's do I have that are indistinguishable, and how many B's do I have that are indistinguishable? And this turns out to be this factor here. This is exactly the same thing that we derived when we had the frogs and hearts and yellow widgets. The total number of A's and B's is n. I have m B's and n minus m A's. And so I can calculate this coefficient. Well, there we have it. That's the binomial theorem. A plus B to the n power is just simply equal to the sum of all of these terms. And we can see here that the A, we have the correct power for the A and the correct power for the m, and then just simply how many different ways we can arrange the A's and B's turns out to be our coefficient. But let's go on with this, and let's see something else here called the Pascal's triangle. First, let me just talk about some properties of Pascal's triangle. Any cell, like this green cell, is the sum of the two cells above it. And so 15 is equal to 5 plus 10. That's pretty straightforward. We can also write this in our computational notation. Actually, I probably hasn't defined that yet, have I? Bummer. Well, I'm going to move on anyhow. Any row is the coefficients that you find on an expansion of A plus B to the n power. So A plus B to the third power, we have the coefficients 1, 3, 3, and 1, and sure enough, those are the values in the Pascal's triangle across this. Here we go. Here I define this combinational relationship here. So remember the binomial theorem, we had n factorial over m factorial, n minus m factorial, and that was the coefficient on one of the terms. Well, a lazy way to write that is just m over m with brackets. It's just a notation candy, so that's all. Well, I can calculate the value in a cell by just simply knowing what row and what column the certain element is in, which this makes sense because I just told you that the coefficients for the expansion of A plus B to the n are the values that are found in the Pascal triangle, And this is how we calculated the coefficients in the binomial theorem. So it makes sense that you can calculate the values in the Pascal's triangle using the same relationship. The sum of the values across any row is equal to 2 to the n. And surprisingly, this is as easy as 1 plus 1 is equal to 2. Let's see. This is the binomial expression that we've had before. Let's let a and b be the numerical values of 1. So a is equal to 1, b is equal to 1. So I put 1 in there, and of course 1 plus 1 is equal to 2, and so I get 2 to the n. Let's look what's going on the right-hand side. When I let a and b equal 1, I get 1 raised to a power. Well, what's 1 times 1? Well, it's still 1. 1 times 1 times 1 is still 1. So these pretty much disappear in our product, and I simply get the sum across a row. So I'm summing over the m's, which takes me across the row, is equal to 2 to the n. And so here we have 1 plus 3 plus 3 plus 1 is equal to 8. All right. Now let's just play with the Pascal's triangle a little bit. If I take a large Pascal's triangle and I go through and I color all of the odd numbers red and all the even numbers orange, I get this interesting image over here on the right hand side. Another way of thinking about this is I've taken the value in the cell and then I've colored the cell based on its remainder, right? If the number is even, the remainder is 0 and it gets colored orange. If the remainder is odd, I get 1 as the remainder and I color the cell red. Well, we can do this with 3. What happens if, and when I divide by 3, I have 3 options. The remainder can be 0, 1, or 2. And so I make those color combinations. I could do it with 4. So we'll just kind of buzz through these. They're really just here for entertainment. But it's just interesting that you get these interesting triangle designs. Okay. Well, what about generalizing this to something more complex? What about a plus b plus c plus blah 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 blah, however many letters we want, raised to the n power? Well, using different letters is actually a little bit difficult. Maybe there's a better way to write this. Let's let it be a sub 1, a sub 2, a sub 3, and so we can have out to m a's with the subscript. So I'm going to take that whole sum and raise it to the nth power. Well, first let's talk about a few properties that we expect to know. Well, one is we expect there to be terms that are a1 to the n, a2 to the n, and so forth. So we'd expect to see that, just like we did when we had a plus b to the n power, right? We had an a to the n, we had a b to the n. Well, if we had a plus b plus c, we'd expect that we would have an a to the n, a b to the n, and a c to the n. That's all I'm saying here. All right. Okay, and if we are generalizing to a hyper Pascal's triangle, we would expect a similar rule to apply, where the value in a cell is the sum of the cells above. And we'll see that in a moment. The powers of each term in the expansion must add up to n. Remember when we had the a plus b to the n power? At each term, the powers on a to the b added up to n. And the same thing is going to be true here. Every term that we add together, the sum of the powers has to equal to n. So we have that as a constraint. And the coefficient on each term is going to be the number of ways that we could make that term. It's exactly what we saw before. Okay, so we have all the pieces. Let's first let's play with an idea here. Let's see if we can visualize what a three-dimensional Pascal's triangle would be. Well, that was pretty easy. So here is our visualization of a three-dimensional Pascal's triangle. Now, what we have is we have ones down all of the sides. Remember before, when we had our simple Pascal's triangle, the ones were just down the sides, and all of our larger numbers were on the inside. Whereas here, the ones go down the sides of this three-dimensional triangle. Now, if we turn this just right, you can see that down one side is the regular Pascal's triangle. See the 1, 2, 1, 1, 3, 3, 1, and so forth. That is exactly what we have here. 1, 2, 1, 1, 3, 3, 1. All right. But in this case, we have some, these planes. These blue planes represent the same thing as the rows in the regular Pascal's triangle. And we can see that, for example, this 6 is the sum of the 2's that are sitting right above it. Okay, let's take another way of looking at it. What we're going to do with this short animation is we're going to work our way through the Pascal's triangle and watch how the summing works. Well, as we start on the top, we have a 1 and we just go simply down the side. So this first one is pretty simple. And now in the second case, where we have the 1 and the 1 making the 2, here we have this 1 and this 1 adding together to give us this green 2 as we work down the layers. So right now we are looking at 3 layers on a 3-dimensional Pascal's triangle, and we can work our way on down. And now here this 2, and this 2 are all adding up to give that 6. This 2 and that 1 are adding up to give this 3. And we can just kind of work our way down. Let's go ahead and go to the end of this and take a look here. So this 90 is being made up by this 3, this 3, this 30, and this 30. Okay, so we have a general feel for what the 3-dimensional Pascal triangle look like. And now let's take what we have learned and what we've seen before and see if we can write down an expression for a sub 1 plus a sub 2 plus a sub 3 all the way out to a sub m raised to the nth power. Well, what are the things that we know? Well, first we're going to sum up all of our terms. So we have this summation here. We'll talk about a constraint on that summation. We know that each one we're going to have an a sub 1 to a power, a sub 2 to a power, all the way out to a sub m to a power. Now, of course, these powers may be 0, which would be equivalent to having, for example, when we had a plus b to the nth power, the last term was b to the nth power, and the a we can think of as being there as a to the 0 power, right? Because a to the 0 power is just the number 1. Up in the numerator, when we calculate the number of combinations that we can arrange these letters, we have n factorial divided by the number of a sub 1's we have, factorial, times the number of a sub 2 factorial, and so forth. So this term right here is exactly identical to the number of ways that we could arrange hearts, frogs, and yellow widgets. And then we simply have to sum up all these terms constrained with the constraint that k sub 1 plus k sub 2 sum up to n. Now, if we wanted to use a little bit of mathematical notation here, we could write it this way, where this really just becomes a product of many different pieces, and so do the a's up here. So we can use our capital pi sign for a product. All right, and that's, well, okay. So we went to the generalization of the binomial